The world of the sauropods, those colossal, long-necked titans, is one we often equate with slow, high-reaching browsers, patiently stripping leaves from the Mesozoic canopy. We imagine massive, pillar-like legs supporting a body that seemed to defy gravity, culminating in a small head with simple, peg-like teeth designed for little more than raking foliage. This established image forms the bedrock of our understanding. Yet every so often, the fossil record delivers an anomaly, a specimen so far outside the standard deviation that it forces a fundamental re-evaluation of an entire lineage. Our case file today concerns just such an anomaly, Nigersaurus takedi, unearthed in the arid plains of what is now Niger. Now, let's dissect the evidence and solve the case of this bizarre survivor. This animal was, by sauropod standards, a lightweight. Its estimated length was around 9 meters, a modest size in a world dominated by giants like Giraffatitan and Argentinosaurus. But the sheer disproportion of its dental apparatus to its body mass presents a profound and immediate scientific paradox. When we first examined the recovered skulls, what we found challenged every prior assumption about how a dinosaur could process food. The mouth of Nigersaurus was not just equipped with teeth. It contained a dental battery of astonishing complexity and density. Let's break this down with a 2D diagram of the skull's anterior section. The snout is broad and flattened, almost rectangular, contrasting sharply with the narrower, rounded snouts typical of other sauropods. Inside this broad jaw, we discover the anomaly: over 500 individual teeth, organized into columns of up to 9 replacement teeth stacked beneath the single functional tooth in use. To put this into perspective, most large herbivores possess dozens of teeth for grinding. Nigersaurus possessed hundreds, with a replacement rate that borders on the biologically excessive, possibly 1 new tooth arriving in each position every 14 days. This isn't just a jaw, it's a biological conveyor belt of enamel and dentin. The paradox of dental redundancy is this: why did a relatively small sauropod, seemingly built for a light herbivorous diet, evolve a mechanism for such hyper-efficient rapid replacement and such extreme quantity? Why build a 500-tooth factory to perform a job that most of its relatives manage with 50 or 60? The fossil evidence presents the case file, a creature with an exceptionally delicate skull structure. The bone around the jaw is almost paper-thin, paired with a monstrous, continuously regenerating array of dentition. The head was a vacuum cleaner built by an engineer with an obsession for backup parts. The delicate nature of the jaw suggests fragility, yet the dental battery screams constant, powerful use. This structural contradiction is the key mystery we must now investigate. To understand how this dental factory functioned, we must move from simple description to biomechanical investigation. The case of Nigersaurus demands we treat the skull not as a curiosity, but as a complex machine. We're attempting to reverse engineer a 110-million-year-old biological apparatus designed for hyper-efficient vegetation processing. The investigation focuses on 3 interdependent components: the dental battery, the occlusal surface, and the jaw articulation. Component 1. The dental battery, a biological cartridge. Let's begin by analyzing the tooth structure itself. In this cross-section diagram of the lower jaw, we can see the 9-tooth column clearly. Unlike the slicing teeth of theropods or the heavy grinding teeth of hadrosaurs, the individual teeth of Nigersaurus are exceptionally delicate, thin, sharp, and slightly recurved. They are not built for powerful mastication in the traditional sense. Their strength is derived entirely from their sheer quantity and their arrangement. The key is the replacement strategy. The columnar stacking ensures that as soon as the functional tooth wears down, the one immediately beneath it is pushed up and locked into place. This is where we draw a parallel to engineering. Think of this not as a jaw, but as a revolving ammo clip or a cartridge feeder. The dinosaur didn't chew. It maintained a continuously sharp cutting edge. The constant upward pressure from the roots of the 9 replacement teeth effectively kept the functional tooth fixed and ready. The replacement rate is staggering, maximizing efficiency by minimizing the time the animal spends with dull dentition. Component 2. The occlusal surface and jaw mechanics. The second and perhaps most crucial step is to analyze the action of the jaw. By creating a wireframe model illustrating the range of motion, we can observe the unique morphology. The jaw joints are positioned unusually far back and low in the skull. When the jaw closed, the action was not a wide gape and a crushing bite, but a rapid, horizontal, and highly coordinated snap. The occlusal surface, the total area where the upper and lower teeth meet, was a continuous lateral shear. We're not looking at individual teeth acting alone. We're looking at a continuous cutting blade formed by the fusion of hundreds of individual edges. When the jaw closed, the upper and lower arcades, curved and aligned, sheared past each other, creating an extremely long self-sharpening cutter. The thin enamel on the outside of the teeth and the softer dentin on the inside ensured that this action of shearing past neighboring teeth maintained a razor-sharp edge, much like the differential hardening of steel in a fine-edged tool. Crucially, the sheer breadth of the snout maximized the intake efficiency. The rectangular shape meant that Nigersaurus could crop a much wider swath of vegetation in a single action compared to its narrow-snouted relatives. Here, the machine is designed for volume processing over brute strength. Component 3. The skull's engineering contradiction. The final part of our investigation returns to the paradox of fragility. In this CT scan cross-section, we can observe the surprisingly thin bone structure of the rest of the skull, particularly the fenestrae, or openings. This fragility led some early researchers to speculate that the head was simply too weak for robust feeding. However, a deeper analysis reveals a tensile strength-focused design. The delicate, thin bone is not necessarily weak. It is lightweight and adapted to withstand tension in specific vectors. This design choice tells us something vital about the feeding behavior. The animal was not biting hard objects, crushing bone, or tearing tough wood. It was built for high-frequency, low-force processing of soft, possibly silica-rich, ground-level vegetation. When we synthesize these 3 components, the disposable cutting battery, the horizontal shearing action, and the lightweight broad skull, the function becomes clear. Nigersaurus was not a high browser. It was a Mesozoic ground-level vacuum, its entire head acting as an efficient, self-maintaining horizontal lawnmower. The constant need for replacement teeth was not a sign of poor design, but the necessary consequence of its function, constantly processing abrasive material close to the dirt. This doctrine of diagrammatic authority confirms the how. The creature was engineered for speed, breadth, and continuous sharpness. Our biomechanical investigation has established the how. Nigersaurus was a hyper-efficient ground-level cropping machine. But the true scientific challenge, the core of this paleontological case, lies in answering the why. Why did this specific evolutionary path, the massive dental battery housed within a delicate, broad skull emerge? The answer remains a synthesis and verdict, constrained by the limits of the fossil record. We must now apply our controversy clarity protocol to the competing theories. The central debate revolves around habitat and diet, the very foundation of the evolutionary pressure that forged this remarkable design. Specifically, what kind of environment would demand a jaw built like a conveyor belt and a feeding system designed for constant renewal? Hypothesis 1. The low browsing theory, abrasive ground cover. The prevailing and most widely accepted theory aligns directly with our biomechanical analysis. Nigersaurus was a specialized ground-level grazer, evidence for broad snout and shearing mechanics. The rectangular horizontal cropping action is perfectly suited for sweeping up low-lying vegetation. Ferns, cycads, and possibly the earliest flowering plants in a wide arc. Rapid tooth replacement. The 500 teeth and their astonishingly high turnover rate are a direct evolutionary response to the high silica content of the diet. Modern grazers like cows or horses, which feed on abrasive grasses, exhibit similar patterns, though far less extreme. This theory suggests the plant material was tough and often contaminated with grit and soil picked up during the low-level feeding process. The teeth were constantly ground down, necessitating continuous replacement. Evidence against. The main challenge lies in the delicate skull structure. Critics argue that while the jaw was built for low-force cutting, the thin bone framework may have struggled to endure the lifetime stresses of continuous, high-volume grazing on such tough, abrasive vegetation. While the tension-based design addresses part of the issue, the relative fragility of the skull remains a significant point of contention when compared to the robust heads of other grazers. Hypothesis 2. The high foliage theory, the outlier view. A more speculative but intriguing hypothesis proposes that the massive dental battery of Nigersaurus was adapted for selective mid-level or high browsing, not for ground grazing. Evidence for. The slender, slightly recurved teeth could have been used to strip leaves from tough, woody stems. If those stems were fibrous or hard, they would cause significant wear. But the speed and breadth of the jaw might have allowed for precise, efficient stripping of softer preferred foliage, bypassing the tougher material. This theory attempts to reconcile Nigersaurus with the classical image of a sauropod browser feeding not on the ground, but among the mid-level canopy. Evidence against? The jaw morphology fundamentally contradicts this. As demonstrated in our wireframe model, the low articulation point and the extreme breadth of the snout are mechanically ill-suited for precision browsing. They are optimized for sweeping large volumes of vegetation close to the ground, not for delicate plucking. Furthermore, the heavy wear patterns on the fossilized teeth are far more consistent with continuous, ground-level shearing than with the occasional stripping of soft leaves. The verdict, a grounded conclusion. When we weigh the evidence, the logical conclusion is clear. The low browsing theory is overwhelmingly supported by the biomechanical blueprints. The broad horizontal snout, the highly specialized shearing surface, and the rapid continuous replacement system all point to an animal engineered to process vast volumes of abrasive low-lying vegetation. Nigersaurus takedi was not a clumsy, generalized feeder. It was a masterpiece of evolutionary specialization, a precision-built harvester that transformed the basic sauropod blueprint into a highly efficient single-purpose machine. This creature stands as one of the earliest and most extreme examples of a dental battery in the entire history of vertebrates. a solution born from the need to consume endless quantities of tough, abrasive plants. The final verdict. The paradox is resolved by acknowledging that the animal's entire structure was dictated by its food source. The 500-tooth vacuum cleaner was not an evolutionary accident. It was the perfect mechanical response to an ecological niche that demanded non-stop cutting power. And yet, a final mystery remains. Despite its remarkable efficiency, Nigersaurus stands alone. No other sauropod evolved a dental battery on this scale. Why did this bizarre, brilliant solution not become the norm? That, for now, is a question the fossils have chosen to keep to themselves. The case of Nigersaurus is more than a study of bizarre anatomy. It is a profound look into the relentless and inventive power of natural selection. By deconstructing its jaw, we don't just uncover hundreds of teeth. We reveal an elegant, specialized machine engineered to survive within a fiercely competitive world. This single creature's adaptation, a delicate frame built to host a dental hyperengine, exposes a deeper truth. Evolution's ultimate genius lies in its ability to find 1,000 solutions to a single environmental problem, even when those solutions are spectacularly strange. Our investigation confirms that the most successful survivors are often those that specialize in the most extreme ways imaginable. What is your hypothesis? Do you think the massive dental battery was built solely for grazing on abrasive ground cover? Or could it have evolved for high-frequency processing of a specific type of tough aerial foliage? Leave your analysis in the comments below. And if you want to own a piece of this investigation, the detailed 3D wireframe model of the Nigersaurus skull we analyze is available for our patrons via the link in the description.